Thank you very much for coming along. I'm amazed, Sunday AM, there's so many people out in London. Haven't seen that for many years. Before I do start, I do want to say thank you to the organisers of this session. They don't have to do it, but they do it, and it's great. You know, we can all get together and talk about data and machine learning and AI and open source, and that's really cool. So I wanted to not forget the organisers. So this session, we're just going to do a gentle introduction to neural networks. It's really aimed at anyone who doesn't know what they are, how they work, or perhaps has a little bit of an understanding, but just wants a bit of a refresher. So if you're already an expert, this probably isn't the talk for you, and I won't be offended if you kind of go to another talk. If you are an expert, you might find some of the pictures interesting. So that's just to make sure that everyone's here for the right reasons. The reason I do this, actually, is I do find technology quite interesting and fun, but I found, actually, over sort of 20, 30 years, that it's not very well explained. I mean, I did a degree in sort of physics and computer science and stuff, and I always struggle with this stuff because once you got it, you sort of think, why didn't you just say that? Why didn't you just explain it in a way that anyone can understand? You know, you go to the Wikipedia page on neural networks, and it's actually not that accessible. So I kind of find it fun to try and challenge myself to see if I can explain some of this stuff to people who might be sort of 16, 18, 20 years old, you know, at school. Let's see if it works. Not that you're all 20-year-olds or 16-year-olds. What we'll do is I'll get the screen right first. There you go, that's better. We'll just talk a little bit about context of where we are with neural networks today. I'll explain some of the core ideas, and we'll use some really simple, naughty examples, but through those naughty examples, we'll pick up some really interesting points and really valid points which underlie why and how neural networks work. We'll talk a little bit about doing it yourself with Python. I'm not going to talk about particular libraries. I'm going to be talking about how you might do it yourself. The best way to learn about something is actually to do it yourself. And it's not that hard, actually. I amaze myself at how simple it actually is. There's a particular challenge that I had to play with, which is to train a neural network to recognize human handwriting. Most people here will know it. It's called the MINST data challenge. But I found it quite fun, and people can relate to that. And at the end, I'll just have some extra thoughts around how you might take neural networks forward if you wanted to. And I might regret this, I'll try a little live demo where we draw a number, and we'll see if a neural network recognizes it. I tried it last night. It kind of worked, so we'll see. So let's start with a couple of questions just to really get us into the groove here. So I said to my daughter yesterday, who's 7 years old, I gave her these two questions. I said, here's a photo. Can you point out the people in this photo? And she did. She even recognized there might be a person here because there's an arm. And she found that quite easy. And then I said, she can do addition, but I said to her, could you add these numbers up? And she couldn't do that easily. She couldn't do it at all. But there's an important point here, because humans find some problems relatively easy, and humans find other kinds of problems quite hard or boring or error-prone, whereas traditional approaches to computing can do that. You know, the computers came out, calculators which are built to do this stuff. But if you went home and tried to program your computer to find pictures, people in pictures, that wouldn't be quite so easy. So there's something going on there that's different in human brains, in biological brains. The approach to calculating, if that's what we do, seems to be different to, cogs and wheels kind of spinning and adding up numbers. So clearly we want to be able to solve these kinds of problems, and that drove the search for different kinds of computing, different kinds of algorithms. And neural networks kind of fit into that soft computing space. And it's everywhere now. It's really exploded. Self-driving cars, IBM's Watson. You'll have heard about Google. Huge milestone in playing Go, which is quite a difficult game to kind of computerize. Even your smartphone is getting really rather good at understanding what you're saying when you talk to it. And that would have been sort of, really the stuff of fantasy sort of 30, 40, 50 years ago. And neural networks were involved in Google's achievement, so it's driven a lot of interest. So in this next section, I'm just going to go through some simple examples just to illustrate some of the key learning points for neural networks. I hesitated about doing this because the examples are really rather trivial, but I didn't want the example to distract from the key ideas. So essentially what we want to do is to have some kind of machine, a box, a thing, an artificial intelligence, and we want to ask it a question, and we want it to give us an answer, and we want it to think in some way. It's kind of what we do. And in computing terms, you might recognize terminology like input, output, and processing, calculating. Remember, computers can only calculate, don't really think in the way humans do, or at least we don't think they do. It's a debate about how humans' brains really work. But we know computers can only calculate. So let's just imagine that we have a hard problem. It's not really hard, but let's just imagine we have a hard problem, which is to work out the number of miles given the given kilometers. You and I know that's not really hard, but let's just imagine it is. Imagine we don't really know how to solve it. So what we do is we invent a model. Here we've invented a linear model. We suppose that miles is kilometers times some number, a linear model. We think they're proportional. And we have a parameter which we try, a randomly selected initial number. And let's just try it. We put 100 in, times 0.5, we get 50 out. And we know that's wrong, because when we compare it to real life, we've got some real examples of what the answer should be. We say, okay, that was wrong. So that's not great. There's an error there. So let's refine that parameter and do it again. Oh, that's better. Maybe what we've got inside this circle is now approaching a proper solution to this hard problem. Let's try it again. 70. That's gone too far. That's much worse. Let's go back again and just increment that little parameter a little bit. That's the best answer yet. The error is much smaller. So yes, that's an odd example, but what we've illustrated there is the idea of imagining imagining a model of how something could work with some adjustable parameters, and trying it and changing those parameters based on the error. And that's an important idea for how neural networks work. It's a simple idea. Let's jump to the garden and imagine we're school kids and we've collected some bugs and we've measured their length and width, and we found that we've got two clusters. We've got caterpillars and ladybirds. They're sort of shorter and rounder. These are long and thin, so width and length. These are the ladybirds, those are caterpillars. And if you go back to the first example where we had a linear model, it's essentially it's a straight line. One variable is related to another in a linear way. So maybe we can use that model, that idea of a linear predictor, a linear classifier, to help us recognize whether something is a caterpillar or a worm. Well, that doesn't work, because if something on this side of the line is supposed to be a ladybird, it's got some wrong. So we'll do that. We'll do the same approach again. We'll adjust a parameter. We'll adjust the slope, and hopefully this time it'll be better. But it wasn't. We've gone too far, and this third attempt is a much better separating line. So what we've done here, if we did that with a parameter and an equation, we would have a machine, a little classifier, which would successfully identify caterpillars from ladybirds. So when we had an unknown bug, and we'd arrived at this line through some examples before, we'd say, yep, we know what that is. It's wide and it's short and long. That's a ladybird. So that's how that's essentially how little classifiers work. They partition the space of variables, I guess, length, width, or something else. And if something falls into one category, you say that's an object of a certain type, and so on. Again, that's a simple idea, but it's essential to how neural networks actually work. So what I skipped over there was actually learning from data. You train your neural networks with examples from real life, examples which you know to be true. So here's some examples here, just two. I mean, in real life, you had to have training data sets which are large enough to be meaningful, but we're keeping the example simple here. So imagine we've got two examples. We've got something which is wide and short, and something else which is thin and long. And we know that that's a ladybird and a caterpillar because the teacher told us, or the textbook told us. So we've created, we had an initial line, we just choose it randomly, the slope of it. And we know that's not a good separator because it doesn't correctly classify those two bugs. So we want to actually shift that line up. And if we do that, after the first example, we say it's got to be on the other side of that one. OK, that kind of works better. It does actually do the separation. Let's look at the second example, and we want this to be separated from that, and we move the line up there. And that's essentially the process of training that you go through. If you're interested in the maths of how you do that, you could look it up. It's not that difficult. There's what your classifier came out with, the actual output, what it should be. And there's an error, a difference, and just simple manipulation of that algebra, you can work out how much you need to change the slope by. But if you're not sure about that, don't worry. The idea is simply that we're changing that parameter to better reflect the data. That's the training data. But hang on, something wrong there. What we've done is we've looked at each example and only considered that when we wanted to update the line. So essentially, we might have 100 examples, but the line that we end up with is only considering the very last example. So the first example, we moved just over there. The last example, we moved over here. And that means you've disregarded 99 data samples if you had 100. So that's not very good. So an approach to that is to actually be less enthusiastic about updating your slope. You moderate your learning with a learning factor. So your change in slope has a factor in it called a learning rate. And that's useful because over a training exercise, you do take into account all the data rather than just the last data point, and also protects you against data which is bonkers or is an outlier or is an error. And if we do that, we find that with a learning rate of a half, say, we only jump half the amount that we would have. You end up with a much better line. So moderating is good, and that idea is used in neural networks to help smooth the learning that the neural network does and avoid being drawn towards training data which might be wrong. There is another benefit which we'll come to a little later. Another example to think about. In real life, a lot of data that we might be collecting and looking at has a mechanism, a causal process behind it. If the sun is out today, my body temperature goes up. Or if there's a lot of light in London, the number of people smiling goes up. There's a link there. And sometimes there's more than one factor involved, so you have something and something, or something or something. So some people recognize that as Boolean relationships. If I've been fed and I've had a drink, then I'm happy. If I've not had either, then I'm not. So if data did have that kind of process underlying it, we should be able to we should be able to train a classifier to kind of pick that out. And in the picture we had before, it's okay to have more than one input. You can have many inputs. That's okay. And we don't have to go far from that simple linear classifier picture we had before. I've plotted here zeros meaning false, 1 meaning true. People are familiar with that. And I've colored green meaning the outcome is positive or negative if it's red. So if it's and, it's only true if both inputs are true. With the or, I have a positive outcome if any of the inputs are positive. And you can see that a linear classifier, a line, can successfully divide those two categories. And what that tells us is that that simple classifier can learn to classify data which has this kind of mechanism underneath it. Hang in there, there's an important point here. But if the data has a different mechanism underneath it, like an XOR, which means the outcome is only positive if one but not both of the inputs is positive, then actually it seems that a simple linear classifier, a line, can't separate the two successfully. This one doesn't work because there's a red there. Try different combinations, it won't work. And this led people to get very pessimistic about the potential for those little simple linear classifiers, until someone realized that actually the solution is to have more than one of them. And you can see here that actually if you have multiple lines, you're able to divide up your data space pretty much as you wish. So combinations of those simple classifiers suddenly becomes very powerful and allows you to learn to classify much more complicated data. So that gives us a pointer to the idea of connecting those nodes, heading towards this idea of neural networks, networks of connected nodes, which on their own do very simple things. Let's pause on that for a bit and step away and move to looking at nature, because nature has evolved over a long time to do some things really well. And we talked about human brains earlier, they're really rather good. In natural brains, the unit of computation appears to be something called a neuron, and it takes inputs and passes them along and pushes them out the other end to other neurons. That appears to be the basic unit of a biological brain, and they're made up of many of these. And it's amazing, actually. We've got computers out there which have got terabytes and terabytes of memory and running at how many thousands of cycles a second and vast amounts of storage. They're huge. And yet, a pigeon with a brain of 0.4 grams can fly, can feed itself, can navigate, can communicate, maybe play. It can do some quite sophisticated things in such a small brain. If you look at a particular kind of worm, there's a link to where all this information has come from. It's got roughly 300 neurons, and yet it can do some quite sophisticated things. We think we're clever. Humans have 20 billion, roughly, neurons in our brain and nervous system. There are kinds of dolphins with 37 billion neurons, so maybe we're not giving them credit where it's due. But it's, the important point here is, why is it that these relatively simple brains can do things that we think are quite sophisticated and quite difficult to implement with these kinds of computers? And it goes back to that point right at the start. The method of computing is different, and this puzzle was one of the factors in searching for different kinds of computing, biologically inspired computing, to see if we could get computers to be more artificially intelligent. And again, neural networks are partly inspired by how we observed brains in nature to work. And going back to that basic unit, what it does is it fires if the input signals go above a certain threshold. So you can feed it a signal and it won't fire. You turn up the dial and it pings on. That's the mechanism at play. So we could do that with our little nodes, our little neuron. We could have a step function where we increase the input and then suddenly, pop, it goes on. We could have a different kind of smoother function where we turn up the input and it gradually turns on the output. That's quite popular and it's called the logistic function. There's a formula for it. It's popular for several reasons. The maths is quite simple when you play with it. And we believe that nature doesn't really work in hard, sharp ways, but works in much softer, gradual ways. So there's a bunch of neurons connected to each other. You can see signals flowing through. And each of those units, again, going back to our picture at the start, we have lots of inputs. We sum them, we add them up, and then with the answer we say, okay, do we fire the neuron or not? So we apply a function which might be the step function or that smoother logistic function, then we pop out the output. That's what a node in a network is doing. And actually, to this day, that's what nodes in neural networks do. They might vary the kinds of functions they apply, but that's what they're doing. They're collecting whatever's popped into them and popping out an output. So a neural network, finally, each of those units is what we've described. It takes inputs and pops out an output. This one does the same, that one does the same. And they're all connected to each other. In nature, they might not be connected to each other. But when we program this stuff, it's just simple enough to make sure that they're all connected to each other. So you can see here, inputs feeding into a network, and the signals then propagate through into an output. And you can relate this back to the very naughty example at the start of kilometers and miles. We pop in a question, we do some calculation, and we have an answer out, and we hope it's a good answer, and if not, we train it. So let's pause on that for a little bit, because my brain's not like a computer, it gets tired. Okay, let's carry on. So where does the learning happen in a neural network? That's a really interesting and important point. With the very simple example we had at the start, what we refined was the slope of that function, that separating line, the thing that turned kilometers into miles. What's the equivalent here? Well, there's lots of places you could do it. It may be the function that turns the inputs into a node, into an output, the threshold function. Maybe we could play with that and alter that as we train the network. Could do that. Maybe we could turn some of these off. That's an idea. Another idea is to associate a weight, a strength to each of these connections so that the signal that pops out of one has some kind of weighting applied to it to turn it up or to turn it down before it pops onto the next one. And that's valid. You know, I guess some of the other approaches are valid, but that's the one that's become, this approach is the one that's become really prevalent. So each of these links has a weight. If it was 0, effectively it's cutting the link, because any signal popping out of here is multiplied by 0, it doesn't go in there. If it's multiplied by 2, it's doubled. If it's multiplied by 0.1, it's reduced. And when we train, when we say, we've got an output, it's not quite right, we want to change something in the network to try and improve the output, we're fiddling and twiddling with those weights. Actually, there's another important point that I did skip over, and it's worth going back to. Natural brains are really resilient to damage. You can chop out bits of our nervous system in our brain, and we function quite well until the damage is really quite severe. So we can continue to function even with some damage. We can actually recover and adjust the way our wiring works and repurpose some of the wiring. We're also, the way our brains work is really quite resilient to bad input. So if the input is damaged, if I see someone's face, but some of it's missing or blurred or someone's in the way, we still recognize it as a face. And that's quite a powerful thing to see if we can replicate in real computers. And you can imagine here that actually the learning's spread and distributed. It's not one small thing that's doing the learning, which means that if I damage some of this, it can carry on working. Or if the input's not quite perfect, that's okay. You can sort of see a parallel there. So feeding the signals forward just with some numbers, just to be really clear how these things work. Just got an naughty example here of 0 and 0.5, 1 and 0.5. Simplified neural network. We've got a weight here of 0.9. You can imagine 1's popping in and multiplied by 0.9. So what goes into here is 0.9. That's 0.2. So you can imagine 1 times 0.2 goes into here. And actually, 0.8 of 0.5 also goes into here. So you're summing them up before you apply another threshold function. You don't apply a threshold function to the input layer. That's just convention. And you can work that example through. I won't do it now. But it's really simple what's actually happening inside a neural network there. Yeah, sure. Yep.
Maybe I missed that, but why is it several inputs? So each node is automatically collecting different input, or could it also be that several nodes collect the same input but do different things with them? How does that work?
That's a very good question. It's just convention. So you could have one node with lots of inputs, but you would lose the opportunity to treat different variables differently. So you might have width, height, color, something else. If you put them all into one node, you'd lose the opportunity to treat them differently. So here we've kept them separate. We might have 2 variables, width and height. We might have many more. And by not putting them all into one node, we retain the ability to treat each one differently.
But you could also have the case of using, let's say, 3 input nodes for the same input.
Absolutely.
So and then you can do more differentiated things on this one input. Or is that not sensible?
Yeah, you could do that. So are you saying that I could have one input and then do more things with it?
Well, and then I mean, here you have 2 inputs, the 1 and the half.
Yeah.
And then maybe you have several layers afterwards. But could you also have the case where you take these 2 inputs and have, let's say, 6 first nodes in this first layer?
You could do that. Yes, of course. Yeah, you could do that.
One or the other.
Yeah, no, that's a really important point. You've jumped ahead to where I was going, but you're absolutely right. You can have many more nodes with only 2 inputs. You can have 1 with more. You can have 10 and 100 middle layer nodes. You could do that, and the benefit of that is that you're able to learn much more sophisticated models. Whereas if you only had 1 or 2 nodes, you can see that there is a constraint, a limit. I'll come back and talk about that. That is a good point. If you wrote out what happens at each node in terms of, not numbers, but variables, I guess, what you would recognize is that what's happening can be written as a matrix multiplication. So going back, what's popped into here is input 1 times this weight and plus input 2 times that weight. And if I had a bigger example even with a bigger network, I would quickly realize that the input into a node can be written as a matrix multiplication of the weights and the incoming signals. And that, you might think, so what? You might think, oh man, matrices are so boring, had enough of them at school. But actually, computers, some programming languages, are really good and really efficient at doing matrix calculations. So we'll keep that in our back pocket, because you can imagine if this grows to hundreds of nodes, that's a lot of instructions to write out. You know, you can say that is that plus that plus that plus that times that. That would be quite inefficient for us to write out, and actually not that efficient for a computer to process. But if we could summarize that as a matrix multiplication, and if the programming language or your library, I don't know, sort of NumPy, was optimized for doing matrix multiplications, it means that you could do that very quickly, otherwise you'd have quite a lot of computation. It also means we don't have to worry anymore about what the shape of that neural network is. You know, if it's 5 by 4 or 100 by 200, we just write a simpler expression. So let's go back to that point about learning based on the error, going right back to that start with the example of the kilometers and the miles and the error that popped out at the end. We use that error to inform how we adjusted the parameter, the slope of that line. The same idea applies here. We might have a neural network. We pop in some inputs, we have an output, and we compare it to a training example, and we say, it's not quite right. What do we do with that error? Particularly as we now have many places where we could apply it to. We've got lots of links that we could update. Do we split it in half if we've got 2 nodes? We could do that. That's probably an okay way of doing it. What you definitely don't want to do is to say the error only applies to this link, and we just leave that as it is. So this is where actually there isn't probably a very good answer, but there's a heuristic approach, and splitting it is one approach. Another approach is to split the error in proportion to the incoming weights. So if you've got an error, there's 3 weight and a 1 weight. So we can say 3/4 of it goes there and 1/4 goes there. If the weights were equal, then we would split it equally. So that's an approach. It's a heuristic, but it actually seems to work. And you can see here that for internal nodes, the associated error is the proportion of this error following that link and the proportion of this error following that link, then added up again. That's just illustrated with some numbers. I won't do that right now. But again, that calculation of splitting the error and recombining it at internal nodes can be written as a matrix multiplication. And that's really great because we have the opportunity to really efficiently do those calculations with Python and NumPy. So actually, once we've got that error, how do we use it? It's no longer a linear classifier, a linear kind of function that we're working with. So the algebra is a lot more complicated. This horrible thing here is the output of an output node as a function of all the weights inside. This is a 3x3 network. That's horrible. Trying to play with that probably won't be fun, and it isn't. So we'll try a different approach. And this different approach was one of the reasons why neural networks resurged in interest, because people felt actually that training neural networks was difficult before some bright spark had this next idea. So we'll take a bit of a diversion. So we've got this horrible function, this horrible mathematical function, and it's got high values and low values. So you can imagine it's a bit of a landscape. High values would be at the top of the hill. You might have crevices and lumps and bumps. We've said that it's so difficult, this function, to analyze algebraically, to work out, to do anything really with it. If we wanted to, let's say, find a minimum of this horrible function, let's just say, how would we do that? Well, if you were on a real landscape and it's dark, which means you can't see the whole function, it's kind of difficult to kind of work with it globally, what you might do is to switch on your torch and look around your feet and see where the gradient was pointing. So you could work your way down by following the slope nearest to you. That's an approach called gradient descent. I've chosen really simple mathematical functions here, just the kind of quadratic something squared. But to illustrate the point that, yes, we could use algebra to work out where that minimum is, but we won't do that here. What we'll do is use this gradient descent idea to say, we pick a point, we start a starting point, and we want to get to the minimum. Well, what's the gradient doing here? Well, it's pointing downwards, so we take a step down. I could do it again and again. And if we were on the other side, say, where the slope was pointing up, we'd kind of go in the direction where the slope was downwards. And you can see that that would work. Yes, it's not a mathematically, analytically precise way of doing it, but when these functions are hopelessly complicated and you couldn't do them in an algebraic way, this approach is practical, is pragmatic, and in many cases it would get you to the bottom of that curve. Why is that interesting? Well, the error of a neural network, we saw that horrible expression, that's going to be a complicated landscape. And we want to minimize the error, so we want to go down the error function. So we want to take steps to a point where the error is minimized. If the error is minimized, it's probably the best that we're going to get the network to perform. Cool. Actually, let's look at that diagram again. This is simplified because it's only got, say, 2 weights illustrated. But with a real network, you would have many, many weights inside that network, and they would all contribute to that error function. This is just 3-dimensional. That would be many, many dimensions. And you can do some calculus to reduce the error, which difference between the desired output and the actual output. We square it, actually, to make things a bit simpler. And I won't do it here, but it's school-level calculus, just a chain rule. And you can end up with a function which gives you the gradient. So it says the error changes with the weights in this way. And that's not so hard. Once we've got that expression, we change the weights. The old weight is adjusted to a new weight by following the opposite direction of that slope. And we've not forgotten the learning rate. So if we wanted to do this ourselves, that was a theoretical kind of background there. It wasn't that hard, was it really? If we wanted to do this ourselves with Python, again, it's not that hard. You can imagine that we might have a class, an object class, and really we only need 3 functions. An initialization function which sets the size, how many nodes, how many layers even, because you can have many more layers than just 2 or 3. We want to train the network, so we feed it examples and we tell it what the right answer should be, so you can use the error, the difference, to update its weights. And we want to, once it's trained, we want to be able to question and query that network on data that we're really interested in. It doesn't have to be much more complicated than that. And actually, it's probably a good point to mention that Python's really good for this. It's, as you all know, Python's really easy to learn. It's a nice language for the human mind to kind of get into. And there's some really nice libraries which most people in this conference know and love. NumPy, if you didn't know, is really rich. It's got lots and lots of mathematical array functions in there, and it's what we use for matrix multiplication. There's other cool functions inside this library, plotting, visualization, if you're working with images. And actually, for me, I started with Python back in 1998 when we had Python 1.5, I think it was, and the numeric library. And I left it for a few years, came back and found this notebook. It's really, really great because it makes working with Python and doing experiments really, really easy without messing around with source code files and all that untidiness. It's great for introducing Python to beginners. So that looks horrible, but it isn't really. That's the initialize function where We're setting the number of nodes. We're initializing the weights. And you might say, well, what do we initialize them with? Well, random numbers. We started that very first example with the kilometers and miles example with a random initial slope. We're doing the same thing here. We're randomly picking what those weights should be. Actually, it turns out that if you constrain that randomness to a particular range, your learning works better. So some people will have that range between -1, +1. You can be more sophisticated than that if you want to. Won't do the training function just yet, because it's a bit more complicated than the query function, which is really simple. Takes your inputs, applies that matrix calculation that we saw earlier, the inputs multiplied by the weights. NumPy ... is a magic function, and we do that again for the next. We apply the activation function, which we told Python earlier was going to be that logistic one. Do it again for the next layer, and that's your outputs. It's just a few lines of code, and that's taken your inputs, propagated them through the network, and popped them out the other end. You could probably reduce that line to 3 lines, 2 lines if you really want to be concise. But the point here is it's not that complicated. So the training function looks a bit more complicated, but really isn't, because what you're doing is pushing the signals through the network, just like querying, but this time we're using the error, the difference between the targets, the training example and what it actually produced, and using the other matrix operation that we saw earlier to refine the weights inside, and that's it. There's lots of writing there, but in essence, there's not a lot to it. All this stuff is on GitHub if you want to have a play. There's people who can code better than I can, so you might learn better from their code, but it's on there if you want to have a look. So now I'm running slightly out of time, so I'm going to speed up a little bit. The challenge that I kind of played with was the very, very popular, very famous handwritten numbers challenge called the MINST dataset. It's got 60,000 training examples and 10,000 test examples. So what that means is you train your neural networks or some other algorithm that you've thought of on those 60,000, and then you test it on a different set of data, this 10,000. And because everyone's using that set of data, you can compare how well your network or your algorithm works with somebody else's, and people publish their results on the web. If I look at the data, here's one record, and what it is, it's a number at the start. It says 5 here, and then lots more numbers. Let's see what that actually does, what that actually is. That first one is the label. It's saying this is the number 5. Someone's written a number 5, and the rest of the pixel values, there's 784 pixel values, 28 by 28. If I plot them using matplotlib, you can see that's a kind of a 5. You can see it's not perfect, but that's the challenge. How do you get a computer to recognize even imperfectly written numbers? So these numbers are our input to our neural network, which will have an input layer with 784 nodes, 784 input signals. We have to think a little bit about what we want the output to be. We could have probably 2 nodes on the output and have them be binary, representing zeros and ones to count up to 2 goes up to 4, maybe 3 then. But I didn't do that. I just had 10 output nodes representing the numbers 0 to 9, those labels. So for example, if all the outputs were quite small, except this one, it would mean the network thought the input was a number 5, a handwritten 5. Similarly, if that one was high and all the rest were small, that would mean the input was a 0. But this is an interesting one because there's quite a big signal here suggesting what it saw was a 9, but that was not so tiny either. So maybe 4, 9, maybe it was in doubt, maybe it could be that. So that's kind of an interesting thing to keep in mind. So you can play, you can experiment, you can change the number of nodes in the middle layer of a network. You can change the learning rate, you can have a play with that. You can even repeat your training on that data set more than once to give it a second chance and a third chance. Some people call that epochs. And you can see the performance as a result of that change. So the hidden nodes, if you increase the hidden nodes, you can see the capacity for learning goes up, and indeed it does, but the benefits kind of tail off a bit. A massive learning rate degrades performance, and you can see why that might happen. If you're trying to get to the bottom of a well, you're kind of overstepping it all the time. If it's too small, you never really get there. Your learning steps are too small. If you increase your number of epochs, how many times you go through that training data, you can see that your results improve. I haven't really understood why they go down after a long time. But I've left this point in because it's an important one for us to understand. Training neural networks is a random process. You're starting with a random set of initial parameters. So sometimes it will go wonky. So if you're doing this in real life, you've got to run these things many times and take an average or take the best. Because it's random, you might be unlucky and you might have a bad set of starting points and you might end up somewhere which gives you bad results. So that's the reason why I kept that data point in. When I first did this with some really simple code using no more fancy ideas than what we had, what we've talked about, I think I got something like 80% accuracy on that 10,000 training set. That's not bad, actually, for just the simple ideas, no fancy optimizations, no more fancy maths than what we've talked about, and super simple code. This goes up to sort of 96% accuracy. That's not bad. That's kind of competing almost with what professionals do. You can get better than that, but that's not bad. Just another idea to be applied is, if you think about the training data and you think it's written by humans, what you might do is to say, I'm going to create new data from that data by rotating it. So I've got an original, and I rotate it a bit that way and a bit that way to create more data and see the effect of that. And actually, the performance jumped up to 98% accuracy. So that's not bad. So you can do that. I think someone the other day said in a talk, you spend a lot of time in data science understanding and playing with your data and not so much actually pressing go on the algorithm. And this kind of illustrates that point. And if you understand what the data is, you understand that actually it's written numbers by humans who might write it at an angle. So what if we played with that a little bit? Maybe that generates a richer data set to learn from. I'm running out of time, but this is a little something I do want to show you. Many people do neural networks by training them, feeding a question, popping out an answer. But wouldn't it be interesting if we did it backwards? If we had a trained neural network, we had an answer and worked it backwards to see what it thought the question should be? Let's see what happens. So here are the numbers, 0 to 9, pushed backwards through that neural network. Whoa, is that some kind of X-ray of a mind? I don't know. But actually, if you think about it, it starts to make sense. So if that's the 0, and there's dark bits and light bits, what it's telling you is that if the original digit had ink marks in this black space, it was likely to be a 0, combined with the additional factor of the white bit, as in there wasn't a mark in the white bit. So you can see how that's starting to make sense. Let's take another example of a 3. So you can see that there's almost like a 3 shape there, and there's definitely excluded bits. So if there were marks in those excluded bits, that evidence would probably count against that being a 3, and so on. So that's interesting sometimes to do. Many people don't do that. I don't know why. There's some links for you to kind of have a look at. I do this in more depth with a little kind of ebook if you're interested. But let's try a little live example. And for me, this is really satisfying because it proved to me that this wasn't a kind of a cooked up thing. If I can get my password right. Cool. So I'm going to think of a number. Think of a number. Give me a number so we're not cooking it. What's that? 3. OK, let's try 3. And I'll resize that image to 28 by 28. I hope this works. And I'll save that. And then I have a network trained, and I'm going to, previously it was a 4, and I got that right. Right, moment of truth. 3, yep, network says it's 3. Phew, so it really does work. Thank you very much. Yeah.
Thank you, Tariq.
Cool.
We have time for a couple of questions.
They all know this stuff anyway. Hiya.
So you can train a neural network to recognize digits. So let's say you wanted to recognize lots of different things, not just digits, but maybe words and maybe objects and maybe other things. How do you do that?
So you have to really think about encoding and understanding your data. So if it's words, you might think about what's the best way of matching what goes through a neural network and your data. So with the images, that was relatively easy mapping. We had pixel values. With words, the challenge is to think, well, how do I get from the letters of that word to something I can push through a neural network? And there's many ways of doing that. You might have numbers associated with words like banana is 5, queen is 7, or you might have, you might break it down into numbers. So I don't know, because I'm not an expert, but what I'm telling you is that actually the challenge is doing the hard preparatory work of understanding your source data, which in your case might be words, and seeing how that might map usefully to what flows through a neural network.
Thanks.
Was there another question?
Sure. Maybe you can give us some more insights on if you want to do this with a larger image.
Yeah.
So is it always that you do it on a pixel level, and then you now had just 0 and 1s probably, right? Because it was just black and white. How do you then deal with color? I mean, it becomes very big very quickly. And
it does become very big very quickly, and you can have much bigger images, clearly. You can have color, and if you wanted to take account of that color in your neural network, you have to make sure that you're not, you are bringing those signals into the network. So yes, you'd have a much bigger network. You'd have inputs which maybe took the red, green, blue component. It makes the learning harder or a bigger task. So you might have to train for longer. So there's always a balance between too many variables and too many degrees of freedom and a chance to actually learn something useful. So the answer is yes, you could do all that. You can have much bigger networks. You could take into account color. You could have transparency values, and you can even have features that you've invented to feed into a network if you wanted to. There's nothing stopping you from doing that. My example was deliberately simple, and you should definitely do that. I guess my response is that the more variables and the more degrees of freedom you have, you sometimes can reduce your chances of learning something useful.
Do you have, we had that discussion 2 days ago, do you have any insights how people deal with scaling? Because you very nicely drew your 3 into that little box, right?
Yeah.
So that it's at the same scale.
Yeah.
Typically, if you want to analyze a picture, an image, you might have a scale difference of factor 10
Absolutely,
or 20 and so on. How do people deal with that? To me, it's a mystery.
If you're having
you don't know upfront what scale the object is that you're looking for, and if you want to identify, let's say, a dog in a picture, it could be massively different scales. How do you do that?
Absolutely. So it's quite common practice to rescale your images. If you didn't want to do that, you still have to have something common across your images because you're still training one neural network. So you might say, I'm taking samples from an image, or I'm taking other features from an image.
How do you compare them? If you have like this.
Yeah, that is a challenge.
It's totally unclear,
Yeah,
because yes, I can rescale it if I know what's in it, but then I already lost the impact that I wanted to achieve. So there must be some. What do you use?
So what your questions are zooming in on why data science is not so trivial, because a lot of the questions are really understanding the data. So how can I compare images of different sizes? What is it that I have to make a judgment about or an experiment about to see if scaling things to the same size works? If pixel values from 0 to 255 or 0 to 1 work better, whether I get rid of color data. So, if it was me doing it and I'm not an expert, I would experiment to see what worked. But you're asking the right questions that a data scientist would ask. There's no easy answers to that.
Thank you.
All right, thanks. Cheers.